Hello. Today I'll be introducing cylindrical and spherical coordinates, what they are, why we use them, how to derive them. So before we talk about that, we have to first define a coordinate system. So coordinate systems, like a Cartesian coordinate, is to define a point in space. So we know Cartesian coordinates are x, y, z values. So this represents the horizontal distance in the x-axis, horizontal distance in the y-axis, and vertical distance in the z-axis. So this is perfect for functions, since we all, like our lives, we learned y equals to like a function of x, and something like that. That could be really useful since we already have the x, y, and z values. But this falls short when we're discussing different shapes that could be represented in simpler ways. Like we may be able to represent a circle as x squared plus y squared equals to 5 squared, but we can also represent it as r equals to 5. Now extrapolating this to 3D, think about if we're representing something like a pipe, or we're representing something like a spherical system, for example, a satellite or a planet orbiting. This would require sine and cosine of theta to represent its position, and it would just be more clunky in general. So this is why we want to introduce the cylindrical coordinates and spherical coordinates to simplify how we can represent all of these things. Now I will be discussing cylindrical coordinates. So the first thing that we have to know is that P is a point in space represented by r, theta, and z. I've illustrated it in the diagram under here. Theta is the angle at which the projection of P in the xy plane over here is from the x-axis. R is the distance between the pole, which is the point 0, 0, let's call this the pole, from the projection of P in the xy plane. So that's R. And Z is similar to the xyz. So xyz, this just carries over directly because it represents how far the distance is from the xy plane to the point P. Now, how are we supposed to convert xyz into r theta z? So in order to do this, we have to use a few equations. Rather than just looking it up, it's actually pretty easy to find, so let's derive it ourselves. So we know that this is the x, we know that this is y, and we know that because this is the vertical distance from r and theta, we just do this, we can actually find that x equals to r cosine of theta. Because this distance here is equal to the adjacent side of this right triangle. The same thing applies here. This distance y is actually the same as this right over here. So we can use trig again to find it that y equals to r sine theta. And lastly, just z equals to z. Now we can convert it back as well. So in order to find r from all of these things, we want to see how do we get this. So again, this is x, this is y. So because this is a right triangle, as we defined, we can represent it as using Pythagorean theorem. So x squared plus y squared equals to r squared. So that's how we get r squared, and we can just simply represent it as r equals to square root of x squared plus y squared. But we usually leave it in this form. And again, using trigonometry, we can get this is y, this is x. So because opposite over adjacent, y over x, that's tan theta equals to y over x. And z over z once more. So those are the equations that we just got by looking at this diagram and drawing a right triangle. And this is how we determine the position. And let's do an example of that. So let's do an example from Larson, example 1. Let's go straight to converting this r theta z. Let's define it as 4, 5 pi over 6, and 3. So before we do anything, let's graph it to see where this really is. So drawing a coordinate system, we first define r and theta. So we just look at this plane because we only need to focus on the projection onto the xy plane for those two coordinates. And we can see that from here we rotate 5 pi over 6. So let's do that. We rotate a bit far. Okay. So theta equals to 5 pi over 6. And r equals to 4. So r equals to 4. This distance is equal to 4. And z, we bring this guy up a certain z distance. We define z equals to 3. And this is where point P lies. So using the equations that we just got earlier, we can get x, y, and z. So we said x equals to r cosine theta. So in this case, we simply plug in r is 4 cosine of 5 pi over 6 And that gives us -2 root 3. As for y, we defined it as r sine theta, which is 4 sine of 5 pi over 6. And this gives us 4 times 1/2, which is 2. Lastly, we have the z coordinate, and we just carry it over. So z is equal to 3. And we have just successfully converted r theta z into an xyz coordinate. To sum it all up, xyz equals to -2 square root of 3, 2, 3. Now, as I said, this works both ways, so I'm going to be glossing over it pretty quickly. R is equal to square root of x squared plus y squared, as we defined. And this is actually a plus or minus, since r can be both positive and negative, as this was a squared once. And when we take square root, we have to consider both possibilities. So that's equal to, in this case, 1 squared plus root 3 squared equals to plus and minus 2. We also have theta. So tan of theta is equal to root 3 over 1, which is our y over x in this case. And this gives us pi over 3 plus n pi. Lastly, z is equal to 2, as it carries over. So now we can convert rectangular to cylindrical, cylindrical to rectangular. We're going to be applying this to a problem in the equation. So let's say we have something called x squared plus y squared equals to 4z squared. So just like we defined before, x squared plus y squared is equal to r squared. So we can actually substitute this for r squared equals to 4z squared. Now this Cartesian equation was just converted into a cylindrical equation. Now let's apply this to another equation, since this was just a simple application. So y squared equals to x. Let's call this example A, example B. So this is all from Larson. So if we have y, we define that as ry equals to r sine theta. Now plugging r sine theta into this equation, we get r sine theta squared equals to x, which is r cosine theta. This gives us r squared sine squared equals to r cosine squared, and we can move everything to the other side. So we get r squared sine squared theta equals to r cosine theta, and r sine squared theta minus cosine theta equals to 0. Now we can get two solutions from this. So we can get r sine squared theta. Let's do this step first. So this is from here. And r equals to cosine theta over sine squared theta, or that can also be represented as cosecant theta, cotangent theta. So where did this r go? Nothing is lost, because r equals to 0 in this scenario, which is just a point. Now applying the same principle, let's convert cylindrical to rectangular equation. We have this problem from Larson again. R squared cosine of 2 theta z squared equal plus 1 equals to 0. So this is our cylindrical equation, and we want to convert it to xyz. So first we can expand out cosine theta. So this becomes r squared cosine. This is a property. And then from here, after we apply the trigonometric identity, we get r squared cosine squared theta and distribute minus r squared sine squared theta plus z squared equals to -1. Now this is just r cosine theta squared, since we can just take out the squared, minus r sine theta. We can do this because it's a product, plus z squared equals to -1. So notice over here, this is x. So this becomes x squared minus y squared plus z squared. This is 1 equals to -1. Now flipping the signs, we want 1 to be positive here. So 1, this becomes y squared minus x squared minus z squared. This is a hyperboloid of 2 sheets because it has 2 negative signs over here. And that goes along the y-axis. So it will look like something like... So you can see this is how we represent it in cylindrical. This is how we represent it as a Cartesian. So now we're going to be moving on to spherical coordinates. This is point P, and we will define this as rho, which is this distance to this distance. Now, this is the same thing as cylindrical, as we said, theta, but phi is a little bit new. So theta is the projection on the xy plane. So that's how we get this vector here. But phi is just an angle between the positive z-axis, which is this, and the line segment OP. So O represents the pole, and P is this. The angle between those two line segments, the axis and the line segment, that is going to be phi here. So last time we found the arc cosine theta is equal to x. And we knew this because, again, the right triangle. So if we want to convert this into spherical, we only have one more step to take, since this is already in theta, which is shared between spherical and cylindrical, and we just have to find r. So if you look at r here, that's actually, we can form a right triangle right over here. So that would be, make r equal to, well, this is the opposite side of this vector here, or this line segment. So we can represent r as rho sine of phi. Now, I'll come together later. So this is useful for rectangular to, spherical to cylindrical, but in this case, how does it apply to rectangular? Well, we can just directly substitute this in. R into here, we get rho sine phi cosine theta is equal to x. Now, applying the same thing to y, we have, again, r sine theta equals to y, and substituting that in, rho sine phi sine theta is equal to y. Now, let's get the z-coordinate. So this isn't shared between rectangular and spherical. In this case, it is also a side of the right triangle. So this is the same as this right triangle over here with this theta, and this is the adjacent side. So we have to use cosine. So rho cosine phi equals to z. And now we have just gotten the equations to convert spherical to rectangular coordinates. It's kind of the same process of using right triangles. So we know that rho is this radius over here. So if we make this a right triangle, you can see right over here, this right triangle, we can do r squared plus z squared is equal to rho squared. Well, this is quite useful for something like cylindrical, but not really to rectangular. But we already know r squared is equal to x squared plus y squared, so substituting that in, and we get rho squared equals to x squared plus y squared plus z squared. That's our equation number 1. Next, we want to find theta. We already know that from cylindrical. So tan theta is equal to y over x. Using this right triangle over here, focus on these blue numbers, y over x, arctan, that's how we get theta. We already discussed that, so I won't go deep into it. But now I'll be going into how we get phi. So using this right triangle over here, we can see there's an adjacent edge. That's a very clear and defined radius, which is just rho. So technically, we can represent it as arc cosine of adjacent, which is z, over rho. But of course, we cannot use rho in something where we're doing rectangular. That would be futile. But we already know rho from up here, so we substitute that in. So arc cosine of z over square root x squared plus y squared plus z squared. And just like that, we have phi. So we already defined in the last section that r squared plus z squared equals to rho squared. So we can just bring that over here. If you don't remember, it was because this is the two sides that are like the x and y and r, basically. So instead of the actual xy coordinates, we're talking about the right triangle here. So this is our equation 1. Now theta is the same, so we'll just directly carry that over. And phi. So phi is equal to the arc cosine, as we said, of arc cosine of z over phi. And instead of phi, in this case, we plug in r squared plus z squared, which is z over square root of r squared plus z squared. This is how we get phi. Now to convert the other way, similar thing, spherical to cylindrical. We have r squared equals to, so we know r, as we defined, is rho sine phi, because using the right triangle over here, and phi over here, we can see that this distance is the same as this, and this is the opposite, so it's sine. And because r squared, we have to do rho sine phi squared. This is rho, not p. Okay, great. Theta is the same, and z is equal to rho cosine phi, as we defined on the last page as well. This is because we can use the adjacent side over here, and z is the same as this side length. This and this are the same. And just like that, we have our three equations for spherical to cylindrical. Now let's do some examples where we do some conversions. Now, before we move on to the next example, I just wanted to show a few different things that are easily represented using different coordinate systems that are not rectangular Cartesian coordinates. So we've learned how to convert between all of these, but this is like some objects and shapes or surfaces that are simpler with spherical coordinates. So spherical coordinates, obviously, you can make a sphere with it because you can define rho as a constant, and every point equidistant from the origin would be a point on that sphere. But you can also define a plane. So using the second parameter, theta, we can define a plane that's all points that are angled theta away. So everything on this side would be part of that plane, and that we can define it with just a single constant. Same thing with the third parameter, which is phi. We can define phi as a constant, and every single line segment that is an angle phi away from the z-axis would be a line segment forming that cone. And this is a half cone. And the next example, we will explore how we can convert rectangular to spherical and how much easier and more comprehensible that equation will actually be. So to do some conversions, let's start with the equation x squared plus y squared equals to z squared. This is actually a cone, but let's figure this out and why this is. So when we start, we can convert x squared and y squared equal to their respective equations from spherical coordinates. So we get rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Again, I'm just plugging in x and y for the things we just derived over here. Now, that is equal to z, which is rho squared cosine squared phi. Now, by separating out cosine and sine squared, we see there's a common term right here. So rho squared sine squared phi can be factored out, and cosine squared theta plus sine squared theta is left over. Now we know that this goes to 1 from the trigonometric identity. And we get rho squared sine squared phi is equal to rho squared cosine squared phi. Now we can do sine squared phi over cosine squared phi. These cancel out, by the way, equals to 1. And tangent squared phi equals to 1. And this gives us two equations. Phi equals to pi over 4, or phi equals to 3 pi over 4. Now let's look at it from a standpoint of what phi is, right? So phi is this angle over here between the point P, let's call this P1, P2, and this is all phi. So if we have all angles of pi over 4, in this case, then it would actually form a cone, because the cone is formed out of every single line segment here with an angle of phi over 4 with respect to the z-axis. So now let's represent a sphere instead. This is the same thing, by the way, just on the lower half.